Hi, BStat students. We're finally at chapter 9, which is kind of where this course is headed. So, we're going to start doing significance tests. Now, we're just going to cover the basics in 9.1, and then we'll actually perform them in 9.2 and 9.3. So, if you're not 100% sure on 9.1, it'll start coming in the next two sections. Looking back, we've talked about this before. Mr. Barlow claims to be an 80% free throw shooter. He goes down to the gym and shoots 50 free throws and makes 32 of them. Below is a dot plot that is a simulation of percent made for an 80% free throw shooter. So, assuming he really is an 80% free throw shooter, these are 400 trials of 50 shots. And this is Mr. Barlow making 32, which is 0.64. So these three dots out of 400 show us that that's really, really rare if he really is an 80% free throw shooter. If he really is an 80% free throw shooter, he'd probably make closer to 80%, but he's pretty low. So we don't think he's actually an 80% free throw shooter. So if we make an assumption and we assumed he was an 80% free throw shooter and our sample is unlikely that the assumption is true, then our assumption's a bad one. So first of all, we have a significance test with two hypotheses, the null hypothesis and the alternative. Typically, the claim we want evidence against is the null hypothesis, and what we want to provide evidence for is the alternative. So they are about the population, not the sample. So our null hypothesis is what we're assuming, and we're trying to find evidence against it. Now we'll see what that looks like. Does the job satisfaction of assembly line workers differ when their work is machine-paced rather than self-paced? One study chose 18 subjects at random from a company with over 200 workers who assembled electronic devices. Half of the workers were assigned at random to each of two groups. Both groups did similar assembly work, but one group was allowed to pace themselves, while the other group used an assembly line that moved at a fixed pace. After 2 weeks, all the workers took a test of job satisfaction. Then they switched work setups and took the test again after 2 more weeks. So we want to describe the parameter of interest in this setting. So remember, parameters for population. So this is satisfaction of all workers. And we want appropriate hypotheses for performing a significance test. So our null hypothesis is that the workers' satisfaction is the same when they were fixed pace. And then our alternative hypothesis is that our satisfaction improves when they work at the self pace. So this is our assumption that satisfaction is the same because we're looking for evidence to say that there is a change. So the alternate hypothesis is one-sided if it states that the parameter is larger than the null hypothesis value, or if it states that the parameter is smaller. So in this case, we said that satisfaction improved, so it's larger. That would be one-sided. It's two-sided if we state that the parameter is different than the null hypothesis value. It could be larger or smaller as long as it's changed. P-values. The probability that we get our sample statistic, x bar for means, or p hat for proportions, or more extreme is called the p-value. The lower the p-value, the more evidence you have against the null hypothesis. So we use p-values to make decisions about the test. So if the p-value is small, We reject the null hypothesis and we conclude the alternative. If the p-value is large, we fail to reject the null hypothesis and we cannot conclude the alternative hypothesis. So we make this decision by comparing our p-value to a predetermined significance level we call alpha. If the p-value is smaller than alpha, we say that the data are statistically significant at the alpha level. In that case, we reject the null hypothesis and conclude that there is convincing evidence in favor of the alternative hypothesis. We've been doing this the entire school year with our simulations. If it's really rare that the lady could smell Parkinson's, we rejected that she was just guessing, and we can conclude that she actually can smell Parkinson's. A company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use, on average. The company selects a simple random sample of 15 new batteries and uses them continuously until they are completely drained. A significance test is performed using the hypotheses. So we have our null hypothesis is that mu, our average battery life, is 30 hours, and we want to try to find evidence in the alternative hypothesis that the battery lasts for greater than 30 hours. So mu is the true mean lifetime of the new deluxe AAA batteries. The resulting p-value is 0.0276. So interpreting this p-value in context. So the p-value means, in the long run, there is a 0.0276 chance that we would get an X bar so that's sample mean of these new batteries as large as we did or larger. Now, what I don't like about this example is it doesn't actually give you our test statistic, our X bar. So this would help make it a little more easy to understand. So say we take a sample of these 15 batteries and their mean life was 33 hours. Well, this p-value now would make more sense. It's going to be rare for us to get a value this high. So they're saying that if it's a 0.0276% chance that we would get a mean battery life of 33 hours or more, because remember, greater. So if we had a 0.05, we could conclude by saying that since 0.0276 is less than 0.05, we reject the null hypothesis and conclude that the mean battery life is greater than 30 hours. But if we used our alpha level of 0.01, it's not smaller, so we would have the opposite conclusion. Since 0.0276 is greater than alpha, we fail to reject the null hypothesis and cannot conclude the mean battery life is greater than 30 hours. So this would be we don't have enough evidence to show that this mean battery life is greater. Now, remember we used to say, what if we're wrong? Because we use sample data to make our decisions, we could make a mistake. So here are the errors that we could make. If our null hypothesis is true, then we should not reject, but maybe we do reject. Well, that is a type 1 error. This is our wrongly reject is what we always say is type 1 error. Wrongly reject. So let's look at our battery one again. So if we reject the null hypothesis and conclude that the mean is truly greater than 30 hours, then we should not have said that these new batteries are better, but maybe we put them into production and charge more, and these batteries actually aren't any better. So maybe we waste a lot of money on these new batteries that actually aren't any better. So then we have our type 2 error. So this is when we fail to reject our null hypothesis when we should have. So looking back at our batteries, so if we fail to reject our null hypothesis and we can't conclude the battery life is greater than 30 hours, but we should have. So the batteries actually are better, but we don't conclude that. So a consequence for the error would be that we don't have this better battery because we would stop production probably. So which one is more serious? If I'm the company, probably a type 1 error because I don't want to waste all my money on these batteries. So if you think about making a type 1 error, we want to be careful. So we'd rather make this mistake. We'd rather miss out on these better batteries if I'm the company. So if we think about which alpha we should use, well, we want to minimize our error. So we should probably use this alpha 0.01 because we're more likely to fail to reject, right? We're more likely to make this error that's not as bad. So what does the sampling distribution look like? And what values of x bar would cause us to make a type 1 error? So here's our sampling distribution, right, of all these little x bars. Good enough. So that's what these are all going to be shaped as. And assuming that this 30 hours is our true mean length, we should get a sampling distribution centered around 30 hours. However, 5% will be out here, right? These are our rare values. We could still potentially get an X bar over here. However, it would be really rare, but that would cause us to make a type 1 error if we were to reject that null hypothesis with a value out here. It's possible, and there's a 5% chance of that happening. So this leads us into this power of a test thing. The power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level, alpha, when the specified alternative value of the parameter is true. So, what this means is, this is our sampling distribution, okay? Centered at 0.008. I know it's very hard to read. So the truth is our p 0.08. That's our assumed null hypothesis right here at the center. So this is what we would expect. However, we're wrong. The true p equals 0.11, which is higher. So this is what our sampling distribution actually will look like. However, this is what we assumed. So if we look at this, remember this is what I just drew above. This value is that 0.05. This would be our type 1 error if the truth was 0.08. But if the truth was really 0.11, our sampling distribution would be higher, like this one. This point p hat, again it's hard to read, p hat value, our sample, gave us 0.09. And they showed that on this part of the distribution, that 0.09 would be significant. But on this real distribution, there's actually a lot more chance that we would reject. So there's this 0.75, that's hard to read also. That's the area under this curve. So really, there's 75% chance that we would reject because of this true 0.11 center. So what this means is this is the power. The power of the test is 75%. The power is the chance that we will reject the null hypothesis if the true value was 0.11. So to increase power, we increase alpha or our sample size. These are the two things that will increase power. Don't worry so much about this right now because we'll talk about it more in class.